Yeah. Hi, Professor Huang. Maybe we can start.
Okay.
Yeah.
Now, let's start this session. The first speaker is Professor Xueliang Wu. The talk title is The Foundation of Unification Theory and the Project on Gravitational Wave Detecting in Space.
Okay, yeah. Thanks, Chairperson, and also thank the organizing committee for kind invitation. So before I talk, I will take 1 minute to introduce the International Center for Theoretical Physics, Asia Pacific, which was established as a Category 2 center of UNESCO in Beijing. It was proposed by Chinese Academy of Science, National Science Foundation of China, and ICTP Trust. So here is the signing ceremony in 2017 in the State Guest House. And then 2018, we have this unveiling ceremony in Beijing. And 2019, we have this opening ceremony and the kickoff meeting. So during this opening ceremony, we had the first International Science Committee and invited Professor Xiang Yang to give a speech. So Xiang Yang addressed that over the years, ICTP made great contribution to development of science and technology in developing countries. To extend this contribution to cover the Asia Pacific region now is a great wise, not bad idea. So now actually the TIG program is affiliated ICTP-AP. So the content of my talk is about first I will introduce briefly theoretical framework of gravitational quantum field theory, and then describe the hyper-unified field theory and the gauge geometry duality. And then I'm going to the foundation of the hyper-unified field theory. And then I come to the gravitational wave detection, space-based from LISA and TIG. And I will introduce a little bit more detail about TIG project, and the progress is on TIG-1 with K technology test in orbit now. Okay, so 25 years ago, so when I first attended the SUSY meeting here in University of Maryland, so we started SUSY ground unified models. We call the SO10 data 48 U1. Okay, that's data 48 is the discrete symmetry of SU3. So from these models, actually we can build phenomenologically with 4 input parameters. So we can get more than 10 predictions, which consistent with phenomenologically with the standard model. Sure. And then we try to build a possible unification model for all basic forces, including the gravitational interactions. But we still limited within the framework of Einstein general relativity with general covariance. So the question is, how can we describe the gravitational interaction within the framework of quantum field theory? And can we establish theory of gravity not based on Einstein's postulate of the general covariance and the coordinate transformations? So which is totally different from other forces. So that means we need to go beyond the Einstein's postulate on this general theory of relativity. So we try to the theoretical framework of gravitational quantum field theory. So this is the paper in 2016. So we describe such a framework. So our basic consideration is the introduction of bioframe space-time. And that means, so we build the framework of quantum field theory based on the 2 spacetimes. One frame is the globally flat coordinate Minkowski spacetime, so which act as an initial reference frame and characterizing the motions of basic field, just in the spatial relativity. Another frame we call the locally flat, no coordinate graphic gauge spacetime, which functions as the intrinsic interaction frame for describing the dynamics of basic field. So that means the basic gravitational field is not a metric field, but is a gauge type bicovariant factor in the bioframe spacetime. We call the graphic gauge field. So then in this locally flat 4-dimensional graphic gauge spacetime, we can construct the actions for the gauge theory of gravity. And then we use this graphic gauge field as the Goldstone-like boson. So project to the spacetime, the Minkowski spacetime. So we got the interaction, these actions for gravitational interaction within the framework of quantum field theory. Okay, so we can generate the Dirac equation to the gravitational relativistic quantum mechanics, including this gravitational field. What is important to observe? So that in the Dirac equation, we see the 4 components degrees of freedom of spinor field actually determined by 4-dimensional space-time. The 4 dimension to the 4 component, because the requirement of this Lorentz invariance. So in the gravitational Dirac equations, we distinguish the spin symmetry of the spinor field in hyperspace and the Lorentz symmetry in the coordinate Minkowski space-time. Okay, so that means the postulate for this gravitational quantum field theory, the laws of nature, obviously the gauge invariance and also coordinate independence principles. Okay, so that provides a possible way for combining the general theory of relativity with quantum mechanics, and also gave us a new possible theoretical framework for describing the four basic forces. So now with this framework, we come to the hyper-unified field theory. So try to unify all the basic forces and the elemental particles. So hyper-unified field theory we call it. Okay, this is the long papers as a review report. So it says, I found this article original and rigorously developed. Some novel ideas about the unification have been proposed. Although they are validated as guiding principles for the construction of unified series, remains to be investigated. They are interesting in their own right. So the consideration is very simple. We just tried all spin-like charges of elemental particles as on the same footing as the hyperspin charge. I mean, all the quarks and the leptons, they're both spin, helicity spin, chiral spin, isotropic spin, Carl spin, and the family spins are all as the hyperspin charge. Then we express degrees of freedom of all elemental particles into a single column factor in spinor representation of high-dimensional hyperspacetime. So then we establish a coherent relation between the hyperspinor structure of elemental particles and the dimension of hyperspacetime. So this is just the other way around to the Dirac equation. So, and the Dirac equation, that means from 4 spatial dimension to bring the 4 component enter the spinor field. Now we combine all the leptons quarks as a single spinor field, and we ask so how dimension we need. Then we see the hyperspin charge brings about the globally flat Minkowski spacetime, hyperspacetime with dimension 19, when unifying all the discovered lepton and leptons quarks into a single hyperspinor field. So then this 19-dimensional Minkowski hyperspacetime in coordinate is proposed to have the global Lorentz type symmetry, and the hyperunified spinor field belongs to a Majorana type hyperspinor field in a irreducible spinor representation with hyperspin symmetry. We call it SP118, distinguished to the Lorentz symmetry. Then it's key point to distinguish these two symmetries actually, because they operate in a different space. One is hyperspace, another in the coordinate space. Then we take this hyperspin symmetry in the hyperspace to be local gauge symmetry to characterize the fundamental interactions. Okay, then we get this bi-maximum global and local joint symmetry in this hyper-unified field theory. Okay, so then we can build a hyper-unified field theory. So in 2 ways. One is in the gravitational quantum field theory. Another we can project totally to the coordinate space-time. So then we can see the equivalent in the gauge type of gravitational interaction and the geometric gravitational interaction. So we arrive at the gravitational gauge geometry duality. So this is actually exactly. So now, so that is a statement of the hyper-unified field theory, just unify all the basic forces and elemental particles. We want to know more fundamental for this theories. So this means that is the first step we just do for the hyper-unified field theory. We want to understand the more fundamental questions. So that means why the spinor field is the fundamental building block, or why space and time are different, why there's only one temporal dimension, and so on. So to clarify these more fundamental problems in hyper-unified field theory, so we come to think about the more fundamental concept and carry out a more systematic analysis that we call in this foundation of hyperunified field series. So this is actually our new preprint. It's long papers, and in this paper actually we introduced the two guiding principles, which we can allow us to make following issues. So what is made to be the fundamental building block of nature? So what brings about the fundamental symmetry, and which symmetry governs gravitational interaction, and what is the basic structure of space-time? How many dimensions does space-time have? What makes time different from space, and why is that only one temporal dimension? And also, why do we live in a universe with only 4-dimensional space-time now, and why there are leptons and quarks more than one family? So, and also why the leptons and quarks are chiral females, and so on. So this, we just start from the motional property of any functional field based on the action principle of path integral formulation with the two guiding principle. One we call the maximum coherence motion principle, another we call the maximum locally entangled qubits motion principle. Okay, so then we can show a column functional field. So as the fundamental building block is presented as a locally entangled state of qubits. Okay, so here is the maximum coherence motion problem were proposed. So the emission action of real column factor field as the basic matter field in path integral formulation is built to bring a free and continuous motion that concerns only the first order derivative on x with respect to the variables x mu, and then possess maximally correlated motion with involve only the bilinear form of x. And then we propose that each component of x orbits independent quadratic free wave motion. So that is principle, which actually contains 3 postulates. One is the simplest motion postulate, another is the maximum correlation motion postulate, and then a quadratic free wave motion postulate. Okay, and what is the maximum locally entangled qubit motion principle? Then we propose this functional function is given by a locally entangled state of qubits. So then orbit the maximum coherence motion principle with least Q spin charge. So then this for the column factor field to be an entangled hyperqubit spinor field. So which brings the hyperunified qubit spinor field as the fundamental building block of nature, and also in homogeneous hyperspin symmetry as fundamental symmetry of nature. So that actually we also start from 3 postulates. One is the local coherent qubit motion postulate, and the locally entangled qubit motion postulate, and also the least Q spin charge postulate. So let's come a little bit detail. So we just based on unproductive qubit basis, then we can construct the local coherent state of qubits. We call the high qubit spinor field. And then we can write down this action of this hyperqubit spinor field based on the maximum coherence motion principle. And then we will show this, there's 2 parts. One is the motion correlated part, another is the motion independent parts, which we show there's intrinsic Q spin charge, which displays a periodic feature as the mode 4 quantum qubit number, which enable us to classify all this qubit spinor field and the space-time dimension into 4 categories with the 4Q spin charge, 0, 1, 2, 3. So here's details. This local coherent state of qubits as hyperqubit spinor field. Here's this qubit numbers with 1, 2, 3, 4. And then we construct this spinor field, uniquibit, biquibit, and so on. Then we found this Q spin charges, 1, 2, 3, and 0, and compared to the bit spinor field, it has this Q spin charge 0. That's periodic properties, and then corresponding to the symmetries, spin symmetries, hyperspin symmetries, and the Lorentz symmetries, and so on. And for the quibit number 4, 5, 6, 7, 8, then we can Q spin charge from 0 to 0. The periodic properties and corresponding to hyperspace-time dimensions. Their period is 8, and also the symmetries, spin symmetry, Lorentz symmetries. Okay, so we can classify all these quibit space-time dimension and quibit spinor field into 4 categories. We can write down these relations between the dimension with quibit numbers and so on. So then we can explain why the spinor field is a fundamental field. So because there's automatically appearance of canonical anti-commutation relations and the Pauli exclusion principle, we can prove that one directly. And we can also explain where the time and space are different. There's only one temporal dimension, just from this postulators. So then we found to realize standard model of symmetries as subgroup symmetry of hyperspin symmetry. So the entangled octoquibit spinor field is the minimum one. So it has the symmetries here in the 14-dimensional space-time. Okay. So the hyperspace spin symmetry to obtain the standard model of symmetry as subgroup symmetries. This is the minimum one. And then there's the intrinsic Q spin symmetry is SP3, is amorphic to the SU2, which indicates the family symmetry. So that means it's automatically lead to the 2 families simultaneously. So that means we could answer the questions raised by Rabi, who ordered that when the mu was discovered in 1936. That means 2 families is the necessary, is minimal one. And then we can show, so this unified spinor field contains 2 families. So we check the 1 families, and then we found that each family has free motion in 4-dimensional space-time. So another 10-dimensional space-time is
3 minutes left.
Okay. So I just, that means why our living space-time is 4-dimensional. Okay. And then we have inhomogeneous, okay, finally, when unify all 3 families, we need 19 dimensions. There's inhomogeneous Lorentz symmetries and the translation like symmetry govern gravitational interaction. So that is the hyper-unified field theory. So the second, so this we answer all the questions actually raised before, and then we come to the second part to understand the fundamental interaction and the involving universe. Okay. So this we can answer what acts as a fundamental interaction and how does the fundamental symmetry govern the basic symmetries, and what is basic structure of space-time, how does early universe get inflationary expansion, what is dark matter andate, what is nature of dark energy, and what is nature of Higgs bosons, and how to understand solid families, and so on, this part. So that we introduce the gauge and scaling invariance principle and extend this ordinary derivative to the covariant derivative by localizing the inhomogeneous hyper spin symmetry as local symmetry. So we can introduce this field, gauge field, okay? And eventually we want to show, we call this translation like W spin invariant gauge field brings to the hypergraphic gauge field. That is genesis of gravitational inductions. And then we have this coordinate space-time, we can introduce locally flat graphic gauge hyperspace-time from this hypergraphic gauge field. Okay, that's that is no commutative geometry. So in this locally flat graph gauge hyperspacetime. Okay, so we have this from hyperspacetime, and from this gauge and scaling invariance, we can construct this actions of hyperunified field theory. So here is the symmetries: global, local, joint symmetry. Global symmetry is Bangalore symmetry. Local symmetry is hyperspin symmetry. Describe unify all the interactions. So we come to a statement. So such a joint symmetry in biofilm hyperspacetime removes automatically the long-standing obstacles on unified field theory arising from the so-called common Mandura no-go theorem. So it's become the travel no-go theorem. Okay, so the one we hidden the scaling gauge symmetry as a hidden symmetry, we can show this scaling gauge field becomes naturally as dark matter candidate, and this QC spin scaling field serves as the sources for both inflation of all the universe and also dark energy of the current universe. Okay, and in the hidden gauge forms, I mean in coordinate forms, we get this emerging the hidden symmetry, the general coordinate symmetry, and we can reproduce Einstein-Hilbert action in curved Riemann hyperspacetime. This is called gravity gauge, gravity geometry component. So we come to the hidden coordinate space formalism in the locally flat graphic gauge hyperspacetime. Then the gauge the gravitational interaction disappear. So the hypergraphic gauge field becomes auxiliary field. So gravity effect actually from the emerging the non-commutative geometry in the locally flat graph gauge hyperspacetime. So that's called geometry gauge correspondence. Okay, then in the framework of gravitational quantum field theory, we can show this gauge geometry dualities. And then for the Higgs bosons, so all hyperspin gauge field beyond the four-dimensional locally flat graphic gauge hyperspectrum associated with Higgs bosons. So this dimension according to SP13, SO10, SOP5, these family symmetries. So here is the scalar field. And especially for this Higgs-like doublet, actually we have 10 Higgs doublet from the family symmetries. We have this Yukawa coupling terms. Okay, so then we can integrate in the locally flat graph gauge hyperspacetime. We can integrate out gravitational interactions. So as it is auxiliary field, we got effective hyperspin gauge potential. The Higgs part, we get a Higgs potential. And in the framework of gravitational quantum field theory, in the biofilm spacetime, the Higgs bosons as the composite field of the hyperspin gauge field and hypergraph gauge field. Okay.
1 minute.
For solid families, so as we can introduce the chirality correlation discrete symmetry of back dimension with Z2. So we can see the solid families with chiralities and the fourth family like factor like lepton quark status and so on. Okay, so we can show the zero mode as solid families and so on. So we have gravitational equations in gauge form, which is like the Maxwell equation, which is abelian-like, and which equivalent to the generalized Einstein equation in the coordinate space when projected to. Okay, so I briefly say a few minutes about the gravitational wave detections. So from LIGO announced the gravitational interactions, why we need to go to this ground-based and space-based. We have Lisa and Taiji, and so why we need to space-based gravitational wave detections. So the ground-based gravitational wave detection is only narrow frequencies, and also this mass range is very small. So for the space-based gravitational wave detections, it covers a broad spectrum ranging of more than 4 orders of magnitude and probe the evolution of black holes from the early universe. to pick off star formation errors. So here we TIG program compiled to the LISA. So we have these 3 satellites with ambulance is 3 million for the TIG, and for LISA now is 2.5 million kilometers. Okay, so the LISA Pathfinder has already successful tested some high technologies. For the TIG program, we proposed in 2012. So we also have this 3 laser beams with 3 satellites. Okay. The science mission of TIG program is that in general 5 sources. One is for supermassive black hole merging, extreme mass ratio in spiral and the galactic binaural, and also this background gravitational wave, and also the early gravitational wave for ground-based detections. And different from LISA, maybe we focus the sensitivity, we focus on the frequency 0.01 hertz to hertz, which is more sensitive to intermediate black hole binaries, which is called the seed black holes. So we could understand how extreme black hole formed from these seed black holes and so on. And this is roadmap for TIG with 3 stages, TIG 1, TIG 2, TIG 3, with 1 satellite, 2 satellites, 3 satellites. So TIG 1 is launched August 31st, 2019. Now it's still in orbit, actually. And so this we test some high technologies. We also prove the programs works. Okay, so our results published in the Communications Physics and also for the special issues with 26 articles to cover all the high technologies. This is distribution of the pilot and the assembling. And so the result is that the distance measurement, the noise amplitude spectrum density has reached to 100 picometer. The best precision can reach 25 picometer. And for this acceleration noise measured by the readout voltage fluctuation reached to 10 to minus 10 meter per second square. And this acceleration measured by the gravitational reference sensor, so less than 2 times 10 to minus 9 meter per second square. And also this calibrated true threshold noise of the radio frequency ion threshold reached to the 0.15 micronewton. And the residual acceleration of the satellite less than 10 to minus 8 meter per squared. And the stability of the temperature of the satellite reached to 2.6. So then come to our conclusions. The first on-orbit scientific run of TIG 1 showed that the spaceborne environment called one. Okay, so this last, I come to the last year. On-orbit performance of TIG 1 demonstrated the visibility of the pilot. Okay, and then so for more details, we refer these articles. So finally, I want to emphasize the LISA TIG network in space can fast and accurately localize the gravitational wave source and achieves about 4 orders of magnitude improvement on the event localization regions. And also, it allows to measure the Hubble constant can be up to uncertainty less than 0.5% with that. Okay, so from this conference, all of us expect to have 2 sets of space-based gravitational wave detection around the sun. Okay, thanks.
Because there's no time.
Okay, yeah.
One question. If there's no question, we start second speaker. The second speaker is Ian Lewis. He will talk about collider searches, standard model effective theory. Second speak,
So, Yan, is you're here or not?
Dr. Davis, you can speak your talk.
It looks like he's not here.
Yes. So the third speak,
Can we move on to the next?
next, okay. Next speak is Susan Sickman. He will talk about prefix of LHC, include Atlas, CMS, and LHCb. Sickman.
Hello, yes, can you hear me?
Oh, yes, I'm sorry.
So do I get to speak before Dr. Lewis?
Yeah, you can
Yes.
speak.
Yes.
You can speak.
Yes, he
Okay.
said that maybe he will show up like after this one.
Okay, so
Thanks.
let me share my slides then. Just a moment. I hope you can see my slides on full screen. Okay. So I am starting my talk, if you can hear me well.
Sure.
Okay. So indeed, thank you very much for giving me the opportunity to talk here. I will be talking about the physics prospects at the HLLHC. So at the LHC, right now we are producing a lot of diverse results from the current physics data. But at the same time, we are also dedicating some effort to plan the future of LHC with the high luminosity LHC. So this is going to start around 2027. So high luminosity LHC will have a center of mass energy of 14 TeV and total integrated luminosity of about 3 to 4 inverse attobards. And this is actually a great opportunity because we will have a lot of data, and this will mean that we will have lower statistical uncertainties, lower experimental systematic uncertainties, etc. And besides this, we will also have improved detector capabilities, new detectors, and improved detector coverage. So these are great advantages, but at the same time, these will bring also great challenges, such as high pileup and high beam-induced backgrounds and radiation. Therefore, we would need improved technologies in some experimental methodologies like triggering and object reconstruction, and definitely analysis techniques. So, as I was saying, the LHC detectors, together with the accelerator, they are also undergoing various upgrades and updates. So if we look at the Atlas detector, for example, well, I'm not going to go over all of these things, but we will have increased detector coverage, for example, in the tracker and muon detectors. So we will have some new detectors in there, a completely new tracker and the timing detector. Again, upgrades in all parts of all subsystems of the detector. So similarly, in the CMS detector, we will also have new subcomponents and new updates. For example, again, we will have extended coverage in tracker and in muon detectors, and we will have a completely new colorimetry and cap, which will improve our particle reconstruction. So CMS will have an advanced timing detector, and again, improvements in triggering and data acquisition and all sorts of detector capabilities. So in the recent years, there has been a lot of dedicated efforts to study the physics potential that will be offered by the high luminosity LHC and the improved detectors. So I tried to include a lot of references here to these studies and also along the way in the slides, but just to summarize, there was a dedicated workshop in 2017 and 18 with the collaboration of LHC experiments and theorists. And this resulted in several CERN yellow reports, which are really extensive documents summarizing a lot of physics studies, ranging from standard model physics to Higgs and to beyond the standard model physics. So this provided feedback to European strategy for particle physics. Then there were several recent technical design reports prepared by Atlas and CMS. And finally, currently, right now, there's the SNOMAS 2021 effort, and both Atlas and CMS are contributing to this effort with new high luminosity LHC studies. So the focus of all these physics studies are, of course, to continue and improve the current searches. But apart from that, the more important thing is to design new searches that would exploit the new features of the detectors and make use of the large amount of data to develop new analysis strategies that would allow us to access scenarios which are not accessible with the current LHC data. Now, just a few details on how we are actually performing these studies. For establishing the sensitivity to different physics models, we use two main methods. One method is the so-called projections method, where we take a present analysis that was done using the run 1 or, of course, more run 2 data with 13 TeV. And we use the existing samples, existing results, and we scale these results to higher luminosity and cross-sections that are relevant for 14 TeV. And we consider different systematic uncertainty scenarios. Then the second scenario is to design new analysis completely from scratch using events which were generated with phase 2 specific detector simulation. So here we either use a parameterized detector simulation, more specifically Delphis, or GEANT-based full simulation, which is done by the experiments. And another important thing is the treatment of uncertainties. We have various options here, 3 options mainly. Either we use the run 2 systematic uncertainties, we use directly the values from run 2, then we use the so-called YR or yellow report 18 systematic uncertainties, which is a set of reduced uncertainties which are anticipated for phase 2. And finally, we have a case for statistical only uncertainty. So this will come up, you will see these in the report, so I thought I should explain. Now, in the remainder of the talk, I will just go through some prospects for Higgs standard model and BSM physics cases. Of course, just please remember that there are a lot of studies, so I had to make difficult choices in choosing what to show. The rest are in the yellow reports and other references. Now, starting with the Higgs, the most, the first and most obvious thing to look at is the cross-section and branching ratio measurements. And these were done basically by extrapolating the 36 inverse femtobarn run 2 Higgs measurements in various production and decay channels. And here in the plots, what you are seeing is the amount of the uncertainties, the expected uncertainties, and mainly statistical, experimental, and theory uncertainties that could be obtained by combining ATLAS and CMS results. So we can see these for the cross-section and various branching ratio measurements, and the uncertainties are obtained for yellow report 18 case. We see that after HLLAC, the theory uncertainty remains dominant in the most measurements. Now, another next obvious thing to look at is the Higgs coupling modifiers and coupling ratios. So I guess it's familiar that we measure the coupling by a ratio of new physics to standard model, or let's say data to standard model ratio, so that we could look for deviations from the standard model. So these ratios were looked at again from the previous the measurements I mentioned in run 2, and they were extrapolated to phase 2 to a high luminosity LHC. And here again one can see with what amount of uncertainty we will be able to measure the couplings, Higgs couplings to standard model particles, and the modifier ratios there. Now, another very interesting thing to look at is the differential Higgs cross-section measurements. Now, these are again being measured in run 2, but at phase 2, with the increased amount of data, they are going to become more interesting. And ATLAS and CMS both took a look at these distributions and how precisely they can measure these distributions. So you can see a few examples here. The variation of the differential cross-section versus Higgs PT in the inclusive channels, and specifically in the TTA channel here in a special simulation study done by CMS. And then again, here you can see an ATLAS projection study showing the differential cross-section versus Higgs rapidity and number of jets. Another thing which is very, very important and relevant for high luminosity LHC is the di-Higgs measurements and the Higgs self-coupling measurements. So di-Higgs is a flagship measurement at the high luminosity LHC. And there we measure the trilinear Higgs self-coupling, lambda HHH, and by doing that, we are able to constrain the Higgs potential shape and learn more about the nature of electroweak symmetry breaking. And this coupling is also quite sensitive to beyond the standard model physics. So here, what was done, again, there were several studies done by ATLAS and CMS, some dedicated studies, some simulation and projection studies. And here you see the combination of all these results. So di-Higgs will be, we will be able to observe it only at the high luminosity LHC, and we will be able to observe it only after combining ATLAS and CMS measurements, as you see here. So here in the plots, you can see the contributions from different channels and the amount of uncertainties that we are expecting to see at high luminosity LHC. But this is very, very relevant for them. Now, the next measurement about Higgs is the mass, width, and Higgs to invisible. Regarding the Higgs mass, there's no dedicated study yet, but by looking at the object performances at ATLAS and CMS, we are expecting to have a measurement of with about 10 or 20 MeV accuracy. So this will give an improvement of about 10 times more with respect to run 2. Coming to Higgs width, well, the more interesting measurement comes from the off-shell measurements here, and there are already some studies even done at run 1 and now done at run 2. And when we project the run 2 measurements from Z to 4L case, then we will be able to measure the Higgs width with less than 1 MeV precision at the high luminosity LHC, which will be very interesting. Now, the next thing is Higgs to invisible measurements. So these are, again, quite important for beyond the standard model physics because the standard model branching ratio is extremely small, and this channel is a powerful probe for beyond the standard model physics, especially for cases with light dark matter coupling to Higgs. So the current limit on this branching ratio is about 20–25%. Now, these measurements are made in conjunction with a taggable object like a Z, like a forward jet, or a high PT jet, or even heavy flavor, etc. And in this case, the most sensitive channel to look at is the vector boson fusion channel, where we have 2 forward jets plus missing transverse energy. And CMS did such a study, as you can see here, a simulation study where where some different cuts on missing ET were tried, and the performance was seen and measured. Now, the last thing to say about Higgs is the beyond standard model Higgses. Of course, many models predict Higgses, light Higgses, or heavy Higgses, especially SUSY has many candidates. So there were some dedicated studies, projection studies in CMS and Atlas, which looked at these light Higgses and also heavy Higgses. And here you can see the improvements in sensitivity with respect to the run-2 measurements. Now, coming to standard model prospects, I will be very brief here because we are at the SUSY conference, but here the interesting thing for BSM is to look at very rare processes that would help us probe beyond the standard model. One such case is the diboson scattering, so one can probe electroweak symmetry breaking mechanism, and then this is also, quite sensitive to BSM. Now there are a lot of studies done by Atlas and CMS, but the most recent one was from CMS. Oh, sorry, I just realized I changed the slide. Where the polarization was measured, so the different polarizations, longitudinal and transverse polarizations were measured, and the cross sections were extracted. So here you can see again the accuracy with which we can measure these processes. Now, again, coming to rare processes, this time 4-top. 4-tops would be quite an interesting measurement. And again, there was a projection from CMS. So we can see the expected significance versus luminosity for different types of cases of uncertainties. And, when we are able to get rid of the systematic uncertainties, we can see that we'll be able to measure things much better. And the other thing is the associated production of top pairs with W's, Z's, and photons. And again, there are some plots showing the uncertainties and the measurement capabilities of Atlas and CMS. Now, in the final part of the talk, I will go through some beyond the standard model prospects, of course, mainly focusing on SUSY. So there were plenty of studies done by both Atlas and CMS. So let's start with going over the more classical simplified model plots that are showing the expected reach for gluinos and stops. So here on at the top, you can see a study done by Atlas looking at the projections of stop pair production. The Atlas was looking at both the large delta M case and also the corridor case. And here you can see what kind of an improvement we would get over when we do these measurements, or let's say the searches with phase 2 data. So a similar search was done by CMS, this time looking only at the cases with boosted tops and W's. So here again, we can see in these plots on the left for gluinos and on the top for tops quarks, how much the abundant data will improve our reach or sensitivity to gluinos and stops. Now, coming to STAUs, these are quite difficult to reach with the current amount of data that we have, but this will again be, they will be much more accessible at the high luminosity LHC. So both Atlas and CMS try to check our reach, and we will be able to have an exclusion reach of about 700 GV with both Atlas and CMS. So we will be able to probe the STAU co-annihilation cases easier with that amount of data. Now, going to the electroweak sector, lightest charginos and neutralinos, Atlas did a very systematic projection of their current run-2 searches for the light chargino 1 and neutralino 2 case in 3 channels here. Chargino 1 going to 2 lepton and missing ET through 2 Ws, and Chargino 1 neutralino 2 in the 3 lepton plus missing ET channel, and Chargino 1, Chargino 2 to 1 lepton 2B and missing ET channel. And here again, the plots are showing how much phase 2 is improving. But again, please remember that the gray areas for run 2 are with 36 inverse femtobarn. So these actually these exclusions got a bit better with the most recent run 2 results. Now, continuing a bit with the electroweak sector, the Higgs-Xenos are quite interesting, of course, for naturalness, and there were dedicated searches to look for these too. So there are 2 well-known ways of searching for Higgs-Xenos. So when the chargino, which is chargino is promptly decaying, we would get low PT soft leptons. And these are looked at the low lepton and large missing ET plus ISR jet search. And when we have long-lived long-lived charginos, then we would go to the disappearing track kind of searches. So Atlas tried both of these, and here you can see the complementarity of exclusion in a plot. Now, going finally to more heavier heavier charginos and neutralinos. So these will only be accessible at the HLLHC, and CMS did a dedicated search at same sign dilepton, well, which comes from the same sign Ws from the chargino to neutralino 4 decays, and looked at the exclusion and discovery reach. This was a search directly designed for phase 2. Another thing that's very, very relevant for especially phase 2 is the long-lived particle searches, because we will have new detector features both at Atlas and CMS, and they will allow us to search for long-lived particles in more diverse and effective ways. So again, several things were tried at CMS and Atlas here. So on the left, we can see displaced muon searches, and I think somebody needs to mute. Okay. So displaced muon searches, when looking for GMSP muons, and we also looked at displaced dimuon cases where we have long-lived dark photons from Higgs decays. So in both cases, CMS did a special muon reconstruction using only the CMS muon system. Then, on the other hand, Atlas looked at displaced vertices in searches for long-lived gluinos, which are predicted in split SUSY models. And they again tried a special displaced vertex reconstruction algorithm in the new Atlas inner tracker. More about long-lived particles. So one thing both Atlas and CMS are intending to have are specialized timing detectors. And these will be very helpful in many things, but especially in long-lived particle searches. And here are 2 examples from CMS. One case is the measurement of displaced photons from GMSP. neutralino 1 decays going to a gravitino and the photon. So the timing detector will be able to measure the time of arrival of photons and discriminate signal from background. And on this plot, you can see the difference that is made by the MIP timing detector with respect to the case when there's no MIP timing detector. And another case is for heavy charge stable particles, this time looking at GMSV tau. The MTD is also going to help us measure the particle velocity with a much higher resolution, and this will again help to extract the particle mass with a relatively high precision, as one can see in the plots here. Now, a few more highlights before I finish. Another thing that's that everyone does at the start of every run is to look at high mass resonances, and Atlas and CMS also looked at our sensitivity to various resonances. Well, there are many studies, but I'm only showing 4. One case is resonant di-Higgs to 4b, and here we have a heavy spin 2 Kaluza-Klein graviton, for example, as a signal model. And in this case, we have boosted BB pairs and large reduced jets. And another thing is TT bar resonances measurement, again, for RS gluons this time, and again using boosted tops and top tagged jets. Of course, speaking of resonances, we always have Z primes and W primes. And in these Atlas plots, you can see that phase 2 is going to bring us higher by 2 TeV compared to run 2 in sensitivity. Another thing is leptoquarks. There are also several studies done looking at leptoquarks. Not really going to go in detail, but here you can see again that phase 2 measurements of leptoquarks are really moving our sensitivity much higher compared to run 2. And the very final thing, dark matter, of course, extremely important candidate, has a candidate almost in every model. And there are many direct and indirect searches, but the most obvious case to look at is to look for, apart from classical SUSY searches, of course, is to look for an invisible dark matter plus some visible mono X particle signature, where this X could be a jet, a photon, a Higgs or Z, or heavy flavor or VBF particles. And the interpretation in phase 2 case is done in a more refined and systematic way. And there are some assumptions made on mediator couplings to dark matter, etc., etc. So there's a systematic effort going on, and HLLAC is going to be significantly sensitive to heavier mediators and smaller couplings. So here you can see 2 cases from dark matter plus monojet and dark matter plus mono Z. And finally, on the right side, these plots I always find very interesting. They show the interplay of the LAC measurements with those from the direct detection searches, and we can see how LHC is complementing in the lower dark matter mass cases. So this brings me to my summary. HLLAC will offer an unprecedented amount of data and new detector capabilities, and we're doing extensive studies to be well prepared to make the most of this data and figure out the performance of our detectors. And I was only able to show just a handful here. The rest is in the references, and the studies are going on. We will continue this work in the SNOMES 21 effort, and then it will become much more central during and after run 2. Thank you.
Any question or comments? Any question or comments?
Hello.
Hello.
Okay.
Okay.
Okay. Hidaka. Dr. Hidaka.
Yeah.
You
I
speak.
have a question about coupling modifier precision.
Please,
Yeah.
almost there. Yes, this one.
Yeah. And is this a global fit result, or you just modify one coupling modifier, fixing all the other coupling modifier, or global fit?
This is global fit to my knowledge.
Also for branching ratio, the next previous page.
I think so,
Ratio
but
page, you
I
have
think
a
so.
branching ratio precision.
I think so.
They are all, this is the branching ratio. This is the branching ratio
Yes,
precision. They are all global fit.
I think so, but let me check after the talk and put it in the chat window to confirm.
Okay. Okay, and assuming some model, I think. This is model dependent global fit result, I think.
I think it is not. It's not model dependent. There were also some effective model cases done, but this is really the simplest case, where there are no assumptions on the model.
I mean, assuming no beyond the standard model mode, and assuming no excess of invisible branching ratio, you have to assume something, okay?
Yes, that is true. What I'm saying is
that is model dependent analysis.
Yeah, that is true. What I meant to say is that there's no specific assumption on beyond the standard model.
Okay. Please check. Okay.
Yes, I will check and put it on chat window just very shortly.
Okay. Thank you.
Sure.
Any more question? If there's no more question, let us thank speak.
Thank you very much.
The next speak is Alexander Dmitry Fuska.
Hello, Professor Wang. Maybe you can say connect to like Ian Lewis. He's online right now.
Yeah.
Who?
I made it.
Ian Lewis.
Yeah. Oh, okay.
Oh,
yeah. And Lewis, come. Okay.
Yeah.
The next speaker is Ian Lewis. Please start.
Okay. Can you see my slides? Can you hear me?
sure. Yeah. Sure.
Yeah. Okay.
Yeah.
First, let me apologize for not making the other one, but I've been invited to talk about Collider. My deepest apologies for that. So this is for Collider searches in the standard model EFT. So first, what I want to talk about is why we want to do EFTs, and I'll go over what EFT is a little bit and some results I find interesting. Mainly, as we've heard, unfortunately, the LHC really hasn't discovered any physics beyond the standard model at this point. And hopefully that will change in the near future. We all want that. However, even though we haven't discovered any new physics, we know the standard model cannot be all there is. There's dark matter, there's the baryon matter, the matter-antimatter asymmetry, various problems with the standard model. So we have to know there's new physics to make a series of assumptions, basically that the standard model particles and symmetries so far appear good and valid at the LHC. And so all new, and then you make another assumption that all new physics is heavy and inaccessible at the LHC. And from that, you'll get an EFT. which I'll go over soon, but basically what happens is you integrate all the new physics and you get effective operators consisting of standard model particles and standard model symmetries. And these end up being very versatile. So there's a set of assumptions. So if there's like new physics, the standard model EFT doesn't work so well. But the nice things about it is, first of all, since it consists of standard model particles and symmetries, it provides a systematic parameterization of any deviations from the standard model that are basically more or less consistent with the standard model particles and symmetries. So we can try to understand how these anomalies would show up in data, put limits on the anomalies, and so forth. The other thing is it provides a consistent theoretical framework to combine multiple measurements of standard model processes against experiments. So you can take all of the LHC experiments, you can combine them with LEP, you can combine them with flavor, and since you have this guiding principles, you can combine all these experiments in the self-consistent theory. And based on all that, it provides a framework to search for anomalies in the standard model processes, because you can combine all these measurements all together across all different distributions and processes, and see if there's some regions where something starts kind of showing up with certain types of processes or certain type of operators. And through all this, the parameters is how well we can measure the standard model. It puts a nice quantification on that besides just error bars, because it puts some sense on the bound of the scale of new physics the current precision measurements are sensitive to, so we can kind of make sense of the error bars on standard model distributions and error bars on precision standard model measurements. And we learned a lot of information from this. So the effective field theory, it's quote unquote model independent formulation of deviations from the standard model. I say model independent because you assumed everything is heavy and you only have standard model like particles. You can break that pretty easily. So as I said, the philosophy is that we know the standard model is good at the 100 GeV to 1 TeV scale with a very standard model like Higgs boson, and we're going to treat SU2 cos U1 as a good symmetry. And so the standard model effective field theory is just basically a power expansion of this 1 over lambda, where this lambda is the mass scale of my heavy new physics. And then all of these operators I make consistent with the standard model symmetries, and I can just make a power expansion 1 over the high physics new physics scale. Good. And then I can put bounds on what these Wilson coefficients are, and assuming these Wilson coefficients are 1 or 4 pi or something, I get a good sense of what the scale of new physics is from our precision measurements. Good. There are a lot of operators to deal with, and this is just the Warsaw basis. This is dimension 6, and there's a lot of these. You're not meant to read all these, and you try to put bounds on as much as you can, and there's various assumptions you can make about the flavors of the quarks, the flavor structure of the quarks and the leptons, and all of that is important. To basically put assumptions as you get more and more measurements, you try to relax your assumptions or change the assumptions more so you can get better precision on your operator and try to get more regions in the EFT space. And so for global fits, which I won't talk about too much, and there's a lot of these from various groups, from SFitter, HEP fits, there's a new one by Maltoni's group, basically global fits and Veronica Stons and Ellis and company. So global fits, you basically take all the data, relevant data, and you try to fit the Wilson coefficients of these operators, and you take all the known measurements and you try to fit them all. And you try to see what scale of new physics different operators are sensitive to, what operators are we combining, what operators are we putting the most bounds on, how do different measurements consist, how do different measurements bind each other. For example, there are a set of operators that typically we think of Higgs physics, for example, is phi dagger phi, G mu nu, goes to gluon fusion to Higgs. But as was shown by John Ellis and Veronica Sans recently, this actually shows up in top quark physics quite a bit. And so top quark physics can put sensitive bounds on these. And in fact, any operators with the Higgs and the top quarks can put bounds. Top quark physics constrains important regions of the parameter space is oftentimes complementary to Higgs physics. Now that's all useful and everything is nice, but you can actually learn a lot by just focusing on a single process, because you can see how are my assumptions of what operators are important, how are my assumptions about those types of things, how do they play out, and how do the NLO corrections affect these things, and you can look at helicities and all sorts of things like that. And so of particular interest is the electroweak sector, because this is largely for standard model physics. What I find interesting of the Higgs and the LHC is basically you're testing a spontaneously broken symmetry at the scale at which it is broken, which is over 100 GeV. So let me talk about W plus W minus production a little bit. As I said, it's informative, and I'm going to focus on this a little bit. And this is classic because it has this has this trilinear gauge boson coupling. And so if I test that, I'm basically testing the gauge structure of the standard model to higher and higher precision, which is a very important very important to our understanding of physics at the LHC and physics at the TeV or so. And if I have anomalous trilinear gauge bosons, I might expect maybe there's new things in the loop, or maybe I have an extended symmetry at higher scales, and so I get some sensitivity to that. I said EFT, I would focus on, I'm going to actually present these as basically anomalous couplings, which is equivalent to the EFT. It turns out there's a lot of operators that contribute to the EFT, but then there's only 3 independent deviations of the standard model that are consistent with SU2 left invariant. So that's these lambda z, delta G1z, delta kappa z, and those are the only three independent parameters that I could deal with. And so this anomalous coupling language really brings that to the fore, whereas the EFT language, it can get a little lost. Although they are completely equivalent at this point. The EFT maps perfectly onto this. As I said, matching on the EFT, you have a set of operators and there's 5 of them, and you do the matching, and then you only have these 3 independent ones. So you're only sensitive to these combinations of these operators. So even though you have 5, you only have 3 independent ones. And so there'd be, if you try to fit to these 5 operators with these doing W plus W minus production and anomalous trilinear gauge boson coupling, you'd have a whole bunch of flat directions. Now, I talked about the anomalous gauge boson couplings when we showed a while ago, and people are taking care of now, is that the useful thing about focusing on this one process is you have this anomalous trilinear gauge boson coupling that everybody's interested in. You're also sensitive to anomalous quark couplings. And why this is interesting is because LEP constrained these things very, very well. You look at Z decays, you look at Ws, and you can constrain this to be sub% level of the standard model. But you learned something at the colliders because there's energy dependence. And LEP was constraining things at order 100 GeV, whereas at LHC, I'm measuring distributions out to several hundreds of GeV. And it turns out you have these 2 diagrams. They both singly violate unitarity. And so you have a cancellation of the standard model, you add them up, but you have different contributions to anomalous quark couplings. You add them up, you spoil the cancellation, and then you get growth with energy. That will eventually have to be dealt with, but you can search for this at LHC. You try to see if your distributions start rising, eventually hopefully going into resonance, so you can try to see the resonance and actually see the particle later on. And these are just some differential distributions to show that, versus a diquark invariant mass, where now I've decayed the Ws. So the blue lines are for just anomalous 3-gauge boson couplings. You can see over here, you have various things at NLO and stuff, and you get some separation from the standard model. And then you have anomalous fermion couplings on the right-hand side. The standard model, again, is black. The standard model NLO is black. And you can see the anomalous fermion couplings, we've shown points that are consistent with LEP, have about as big of an effect as the anomalous trilinear gauge boson couplings, even though there's a sub% level correction on top of the standard model. In fact, assuming my Wilson coefficients are order 1 GeV, get an anomalous couplings corresponding to about 2.8 TeV is what we chose. So this is high level, high scale new physics. Good, and this is just to show it. You can actually look at the amplitudes, and when you look at the 2 longitudinal couplings, you can see you depend on these anomalous quark couplings. You also depend on the anomalous trilinear gauge boson couplings, and so you get this nice growth with energy. Good. And this is just showing some of the importance of actually doing these fits. So you can do, so if I look at the left-hand side, I can do a 3-parameter fit, which is just to my anomalous gauge boson couplings. I can put the anomalous quark couplings, and you can see I increase the region a lot, and it has a very large effect. It shifts the central value and changes the shape a little bit and increases the region a whole lot. So again, this is looking at a specific process and learning things. So there's a lot of examples of this. For example, recently, Woltzer and company pointed out that for Drell-Yan, you can try to measure angular distribution. Those end up being very sensitive to EFT and that sort of thing. Angular distributions with respect to energy, so a double differential distribution can constrain these, and the measurements aren't really done yet. And you learn a lot by, even though the global fits can tell you a whole lot, if you really delve into one process, You can learn what's going on with that process and what type of measurements you want to do, what effects are we missing, what assumptions in the global fits do we need to relax. Good. So, and then you can look at different differential distributions by helicities. These are just showing the effects for, say, transverse, and you can see the fermion coupling makes no difference, whereas longitudinal, the fermion coupling, which is this green and this maroon, makes a big difference once you do longitudinal, and that's just what I showed with the amplitude. It shows up in the longitudinals, but not the transverse. And that makes sense because the longitudinals are where you start getting the growth with energy. And so again, trying to measure the helicity information can start telling you information about the anomalous fermion couplings versus the anomalous 3-gauge boson couplings, and you learn some information. Future colliders, you can try to do this. This is all LHC. You can try to look at this at the HE LHC. So this was for 27 TV. We did this a while ago, but you should see something similar to 100 TV. And basically, we only consider the last spin and consider some statistical and systematic uncertainties and put some cuts on our leading lepton PT, just so we're living in the last spin. And we wanted to see what happens when we do these global fits. And we scan over all the allowed LEP regions. You can see again, you have the 3-gauge boson, which are these black and red regions. And then you add in the 3 fermion, you add in the fermion couplings, and all the regions shift, and they shift, the shapes shift a little bit, the central values shift a little bit. The central values are non-zero here because it turns out LEP had a non-zero value for this delta GRZD at about 3 sigma. And so to compensate for that and try to hit the standard model, you needed a non-zero value for some of the anomalous trilinear gauge boson couplings. And then this just becomes more pronounced at 27 TV. So if that LEP anomaly persisted, you can see you have very big effects from the fermion couplings, and you start getting something very far off 0. Okay. And that was assuming that you have this non-zero value. And now if we just force all these values, central values, to be 0, and you redo the fits, you can see everything overlaps, but you still get a big effect, and you relax your constraints quite a bit, which allows for new physics scenarios to be at a lower scale than you might have expected without these effects. And so you learned something important again, that maybe there could be new physics there that you thought was ruled out, but it turns out the problem was your assumptions going into your fits. And then 27 TV, of course, it's more constrained, more pronounced. Again, we can look at NLO QCD corrections now. These are just some differential distributions of the PT and the W. So first of all, if you look at fully transverse Ws, there's little to no effect from 3-gauge boson or the fermion couplings. Again, this is a non-interference effect that Contino proved several years ago, that basically there's not interference for the transverse polarized between the standard model and the EFT, or that the interference dies at high energies. And you can see at NLO, we verified that still happens, and the standard model aligns with everything else at 1 over lambda squared. So just keeping the dimension 6 terms consistently. And then if you start looking at different helicities, again, you start gaining information. So you have a pretty big effect when you look at transverse longitudinal, a lot of variation between the different scenarios. So if you can start trying to tag the helicities, you can learn some information. And then if you have fully longitudinal, you get a little bit of a variation. Again, of course, it's small again, because I'm only going over to 1 over lambda squared. Not much change. So again, not much change from the leading order story for longitudinal transverse and longitudinal, but you still get separations. If I go over 1 over lambda fourth, of course, I start getting that growth with energy, and I just get more and more effects. And in fact, if I look at it 1 over lambda fourth, I really learned something that for longitudinal transverse, the anomalous trilinear gauge bosons and distinguishable from standard model, but the separation between anomalous quarks persists. So basically, if I look at the NLO 3-gauge boson, so this blue line, that's exactly the standard model. So I had separation in leading order. But when I go to NLO, I don't have the separation anymore. And I learned that basically that's an artifact of cutting off my calculation, whereas the fermion difference persists. Of course, I kept 1 over lambda fourth, which is why I see such large effects. And then for longitudinal, almost all the K factors is unity, and the leading order and NLO stories stay pretty much the same. you can try to look what happens to the fits, and there was some nice results recently. This is what we did, but some nice results from the Smith fits collaboration, I believe, where they looked at global fits with the NLO correction to show they make quite a bit of a difference. And this is just our recent results, which are published now. It basically show if I go from leading order to NLO, it affects my results, and I have to include them because it starts affecting my limits. And if I just look at the 3-gauge boson without the fermions, I get quite a bit of a bigger effect. And you can see this across all my plots, across all the anomalous trilinear gauge boson couplings. And in fact, the shapes change quite a bit as well. And this is profiling over the additional parameters. And you can start delving into the effects of 1 over lambda squared as well. And you look at this, you have the leading OR results, you have the NLO results in blue, the NLO 1 over lambda to the 4th, and this dotted line, and you can see the 1 over lambda to the 4th, including it, changes the results quite a bit, which is not surprising because this is where we get all the large growth with energy, 1 over lambda to the 4th, and it's basically telling we're not quite consistent yet. And the shaded region are just various checks on our validity of our standard model. So for example, the gray region leading order cross section goes negative, and the blue region, the NLO cross section goes negative, and we know it can't go negative. It's an artifact of keeping the 1 over lambda to the 4th, not the 1 over lambda squared. And so I can't really live. So if I want to do the 1 over lambda squared, I can't live in these regions. It basically means I have to go beyond dimension 6. And you can see the effect across all of them is pretty pronounced on the right 2 lines, and affects the types of regions I'm sensitive to. Good. How much time do I have left? Do we know? Okay. And then we have, I wanted to comment on the sum because I talked about linear versus quadratic. So this is keeping 1 over lambda to the 4th. And that's quite a big effect, but not on everything. So this is a fit to all these different types of parameters. And you can see the linear expansion is blue. The red is a global, so including all the measurements, all the operators and LEP and everything. And you can see it affects different regions in different ways. So for example, for these operators consisting of just the gauge bosons and the Higgs, you can see the linear expansion doesn't really work, and all of your power is coming from 1 over lambda to the 4th. But when I start trying to look at different operators with, say, Higgs and quarks, the 2 limits are pretty similar, which means basically the 1 over lambda to the 4th isn't making a big effect, and my truncation and my expansion to 1 over lambda squared makes sense. And then at the bottom, what you can see is when you include the 1 over to the lambda to the 4th in your amplitude, you get multiple regions. You get multiple best fit points. And this is just because now my cross section is a quadratic equation instead of a linear equation, my Wilson coefficients. And so I can live in these different regions, but then the linear expansion breaks that degeneracy. And that's really where I want to live, which is right on top of the standard model. And for F mu, again, you can see that basically the linear is actually doing a little bit better than the quadratic. So yeah, so this is just the point that fits for quadratic and linear when the operator is limited by basically precision Higgs or electroweak data, which are these types of things. There's almost no distinction between the linear and the quadratic, but if you're really depending on energy and you're trying to push out to hundreds of GeV or the TeV region, that growth with energy of the 1 over lambda to the 4th really becomes important into these fits. And so you have to wonder whether or not your EFT is valid and whether or not the fits make sense, but hopefully by the end run of the LHC, these can go on top of each other. So I wanted to say quick, just decays and interference resurrection. This is an old story at this point, but there's an importance of decays. Basically, as I showed, that there's a clear indication that different vector boson polarizations depend on anomalous couplings differently. So if I can really tag those polarizations, I can really try to get the anomalous couplings. But the problem is that the bosons decay, and so they're not the final state particles, they're intermediates, and the different polarizations interfere. So the final state, different polarizations interfere. So you really have to include the decays to try to dig it out. As I said before, also there's this theorem basically that the interference at dimension 6 of basically transversely polarized gauge bosons between the standard model and the SMEF. So the standard model goes as 1 over S. The standard model effective field theory goes with S. I interfere those two things. I have no growth with energy. So the interference is not good. I don't learn a whole lot from it. It turns out that if I actually decay the gauge bosons, I can try to get additional information. This was shown several years ago, and people have done this in several things. So they've tried to look at dijets decaying and being collimated. So 2Ws or WZ going into dijets and collimated and doing jet substructure and stuff. And you can start trying to really dig this out. And you can start trying to get these operators, which are really difficult to bound at the linear order, although you can do it the quadratic order. But this interference does it in linear order. So this is just an effect. So this is just basically what you try to do is you try to look at the decay, the
3 minutes.
angle between 10 minutes.
3 minutes.
Okay,
Left.
3 minutes. Perfect. You try to look at the angular distribution between the decay products of your two gauge bosons, and you have some effects. And so this is just looking at basically one is a standard model and one is the EFT. And you can see that your distribution changes at this angular distribution. So if you can really dig that out, especially at high luminosity LHC, you can do a consistent fit to these parameters, not depend on the 1 over lambda to the 4th contribution and the cross section, because that indicates you should include the dimension 8 terms, and then it gets more difficult. The last thing, I talked about all these nice operators. I didn't talk about the dipole operators. Those can be quite important as well. The thing to note about these is you have nice growth with energy and everything, but you have a problem that the dipoles couple left and right chiral fermions to gauge bosons, whereas the standard model couples left and left or right and right to the gauge bosons. And so basically the interference is suppressed by a mass term. And so as you go with energy, it goes as mass over energy. And in fact, the interference with the dipole in the standard model decreases with energy. And for the massless quarks, it's basically non-zero. So everything comes from the 1 over lambda to the 4th. Now you get interesting information in that maybe low energy experiments or stuff like this could be a bit more sensitive to these. You also have interesting things that if you try to look at dipole operators with a top quark, it turns out most of your effects are coming at threshold as opposed to the high energies. If you just look at the interference between the standard model and the EFT, which is kind of breaks down our assumption, our understanding of the EFTs growing with energy as E squared over lambda squared. And so these are just various fits, looking at LHC electroweak diboson production. So the red is for electroweak and the black is for electroweak precision. And you can see the electroweak diboson production LHC is already doing much better than electroweak precision. Of course, this is including the quadratic terms, which is why that's happening. And then you can look at what Gel-Yan can tell you about these types of things as well, because they show up in Gel-Yan. So like UQ bar Z, you get a nice growth of energy as well. And you can see some nice effects trying to look at Gel-Yan data again. So then our old workhorse Gel-Yan tells us interesting information. And so then this is just doing global fits with and without. So and basically there are no flat directions such cancellations with the dipoles. And so you just get some nice fits and you don't get multiple minima. Okay, conclusions. So we really went into case study, but I really want to stress that EFTs are very interesting and that they allow us to delve into our standard model processes and understanding what measurements about standard model processes can tell us interesting information about possible beyond the standard model of physics could show up in precision physics. So we learned a lot about what what tagging polarizations can tell you about it, what looking at, for example, angular distributions and Gel-Yan, as I mentioned, can tell you very interesting information about it. Although the standard model, we know exactly what it is. It's actually sensitive to high scale new physics, and looking at EFTs really tells you that type of information and understanding what type of standard model measurements we can make to try to figure out what types of new physics we can have. And they are highly versatile in that we can combine all sorts of different machines. We can combine LEP with LHC without having to worry about consistency of the data and stuff. It just puts it into a nice global picture into a nice theoretical framework that is intuitive and we can understand in terms of what scale of new physics the standard model measurements actually measuring for us. Okay, thank you.
Let's thank the speaker. Any question or comment? Is there any question? If there's no more question, let's start the next speak. The next speak is Alexandra Dmitrieva. His talk, he will talk about electric weak top measurements at Atlas and CMS. Now start.
Thank you. So yes, I will try to summarize the results of electroweak and top measurements at Atlas and CMS. Second, because it's too much. So we are really trying to push the standard model to its limits. This is, I will try to show only one small selected portion of the results. Of course, we have many more. Now we have enough data actually to have some more kind of precision measurements also for some of the rare processes and even try to probe and measure the anomalous gauge couplings, as you heard in the previous talk. We have very rich program at the LHC, and we are really trying to push and explore the sensitivity to new physics by doing precision measurements, by trying to find unique signatures, trying to do either X searches for loop effects, and of course looking at the differential distributions for and try to look into anomalous couplings. So of course, all these results with Atlas and CMS at the LHC was possible thanks to excellent performance of the LHC as well as Atlas and CMS detectors. And then I have just one slide because this is the first talk summarizing the results of run 1 and run 2 about the performance. So here you can see the two plots. One is the mean number of the interactions per branch crossing. And you can see here all different years that we were collecting data at the LHC. And then on the other hand, is on the right-hand side plot is the delivered luminosity at the different energies for the 5 years that the data taking has been going on. So we have run 1, which was happening in 2011, 2012, where we have total 25 inverse spectrometers of data, and run 2, which will focus, which will be the subject of this talk, which happened between 2015 and 2018. And in total, we have around 140 inverse spectrometers of collected data. So just an overview of the big picture here. So we are trying to explore process rate of over 15 orders of magnitude at different energies. And here, just an example, because this talk is about top and electroweak measurements, you can see the measurements of the inclusivity bar cross-section as a function of energy. And then, right, with the overlaid NN log plus next to leading log theoretical calculation. And if you look at on the 13 TeV data, you can see that the precision of some of these measurements is actually better than the theoretical prediction. On the other hand, right, we can look at all these different processes of large orders of magnitude of the production cross sections of the standard model. And then you can see that, right, we are here at the very end where we have 10 to the minus 3 picobarn for the cross section, and we actually have with run 1 and run 2 data on the order of 100 events for these very rare processes. So we are really trying to get to push the standard model to its limits and try to are sensitive to the rare processes as well. How I am structuring this talk sorry. So as I said, I put the links here at the top of the page for the full list results of the Atlas and the CMS side. How I'm trying to structure the talk is that in a way we can define the results in three categories or in three regimes. So the first one is where we have the precision measurements. So here, these are the measurement of the standard model parameters of the mass and properties of WZ and the top part, as well as the electro weak angle. And as an example of this measurement, we actually have the measurement of the lepton flavor universality. Then we have a second regime where it's just a measurement. In a way, it's not, we don't have enough statistics to be a precision measurement. So here we can categorize the processes from dye bosons. We can look at the differential distributions to probe anomalous couplings, as well as vector Gaussian fusion, associated production of TT bar plus ZW and gamma. And then here is the list of results that I will talk as representative of this category. And then it's in a way an evidence regime where we have very rare processes, so like tribosons. We have representatives of four tops or a flavor changing ultracurrent, as well as vector boson scattering. And then just to get a feeling of which order of magnitude we are talking about, I try to put this scale with the cross-section and where we are with these kind of measurements. So I'll start. The first is the charged lepton flavor violation. So this is an example from the CMS. So here we are looking for opposite charge opposite charge electron and muon pair plus number of B-jets. And we use BDT to try to differentiate the two signals from the background. And here you can see the two example plots, how the BDT is separating the signals from the background in two different channels. One is with one B-jet and the other is more than one B-jet. And of course, here we are trying to emphasize that, right, on top of the processes where we can probe with the TT bar, it's also important that we have a single top processes to show the charge lepton flavor violation. And the vertex we are looking at is marked with red. And here in the table, you can see the measured cross-section and the observed one, the expected and the observed cross-section for two different channels, right? When we have the U and the C channel, and what is the type of interaction, if it's vector, or scalar, or tensor. And then from the limits of the visual coefficients, which are showed here at the bottom right side, we can confirm them to the limits to the quark branching fractions, and then you can see the numbers here, again, for the different channel, and if we are considering the type of scalar vector or tensor. And you can see the representative, these results represented with a diagram of the top right-hand side plot, and we don't see any excess of standard model expectation, but these are most restrictive bounds on the limits up to now. So it's a very interesting measurement. So, so we are setting basically the limit for this process. Then the next measurement, which I want to talk about, is the flavor changing neutral current. And then here there are two channels that we can look into. It's top plus Higgs, where Higgs, in this case, the case diphoton, and then on the next slide, I will talk about the measurement for Higgs, the case to BB bar. So here again, we have the two Feynman diagrams and the processes we're looking into. At the final state, we had the Higgs, which is the case to two photons and jets and leptons. We are using the multivariate machine learning to separate the two signals from the background. And then, right, we can extract the signal from the invariant mass of the two gamma and you can see here how it looks like for the two different channels. So for the U and the C channel. And we can extract the branching fractions for these two channels, and you can see that one is around 1.9 and 7.3 10⁻⁴. If we look at the different channels, so when the top decays to BB bar, again, here we have a slightly different final state. We have 1 lepton and at least 3 jets, from which 2 are B jets. And here we have 5 categories, depending on the number of jets and B jets. What is interesting here for this analysis is that we are using a deep neural network, and this is used to associate the reconstructed objects to the matrix element of the patronic final state, and then we use BDT to separate the signal from the background. So in total, there are 5 categories, and the effectiveness of the BDT and the signal of the background separation, you can see on these 2 plots, where one is representing the channel where we have 3 jets from which 2 are B, and then in the other case, we have 4 jets from which 3 are B. And again, we can set the limits, and we don't see any, for the 2 different channels, we don't see any access over standard model. We can also look at boosted topology. So here, as an example, is a boosted TT bar where we have 1 lepton, 2 B jets, and 1 top tag large jet. So this is with R equal 1, which contains B jet inside, and we have actually this high. We are looking at high PT region, so we have a cut-on on the disperse energy above 355 GeV. And here the main background is single top and associated TT bar production with boson. So as you can see from the top left hand side plot, where the inclusive cross-section is compared to different Monte Carlo predictions, you can see that all the Monte Carlos are over predicting what we're measuring. And actually this is something that we checked, and if we compare the measurement with NNLO QCD plus NLO electroweak, this improves the agreement of the data. Of course, right, in this case, we are looking at very boosted topologies. So this is why we really need high theoretical calculations. And from this, right, we can set from the differential, looking at the differential distribution of the hadronic top PT, we can set the EFT limits, and you can see the extracted values for the Wilson coefficients, and it's in agreement with the standard model. Interesting analysis is the 4-top analysis. Of course, now we have enough data to actually look at the 4-top as well. And here in the final state, we have electron or a muon or opposite sign lepton pair plus any number of jets. And here, right, as a main background that's shown on this diagram here, we have TT bar plus BB bar. And in order to separate the signal from the background, we use BDT, and you can see that there are all these different regions which are depending on how number of jets and number of leptons, which are used for as controlled validation and the signal regions. And here, right, we see the signal strength is twice is 2 from these different 2 channels, and the expected, the observed significance is a bit shy over below 5 sigma, so it's the combined one is 4.7 sigma. And here, what I want to explain on this plot is what is the number of the observed over expected events yields as a function of this logarithm of signal over background. So right, we extracted the number of signal over background for all these different categories, and then put them on the x-axis of this plot. And here you can see as well when we have the signal strength of 1, which is with the orange line, and the signal strength of 2.2, which is the best one, and where the data goes in between. And the measured cross-section of the 4 tops is 24, in the combined channel is 24 inverse femtobarns. Yeah, my slides are actually changing slowly. So the next measurement I want to talk about is associated production of TT bar plus Z or gamma. So here with this channel, we are trying to probe TZ or T gamma coupling. And in the final state, we either have 3 or 4 isolated leptons, or we have a gamma opposite sign electron and muon two jets, from which one is B jet. And here you can see that we can measure the inclusive cross-section at the level of 10% for TTZ or 7% for TT gamma. So in this case, right, you can see that the differential distributions of the PTZ and PT gamma, and that we can also start looking into EFT interpretation. Then switching on to the precision measurement, the only one for this talk is the lepton flavor universality. So actually, this is a novel technique which uses TT bar events and then looks into the double decays to taus muons. And right, we have prop muon, and we are using the fit to the T0 parameter to separate the muons coming from the Ws and from the taus. And here you can see how the DD0 distribution looks like in post-fit fit for one of the channels in one PT region. What is interesting here is that actually we have a precision better than at lab. So on the right-hand side plot, you can see all the measurement of all different experiments, and then how this compares to the Atlas one, which is the most precise one. And right, if we look at the ratio between the tau and the muon branch ratio, the Atlas measurement is actually at 1%, and it's more precise than lab, and it's in agreement with standard model. So the full result is 0.992. And then we can also look at the W branching ratio by combining, by doing a simultaneous fit of subletting lepton PT using these different processes. So from looking at TT bar, T plus W and WW events. And we can look at the leptonic and hadronic branching ratios. So right, in the final state, we have either two Ws or W plus jets. And then you can see here what are the measured branching fractions for electron, muons, and taus. And then how that compares when we just plot them, one as a function of the other. And then here, what I want to stress on the right-hand side plot is basically the Atlas result that was shown on the previous page is shown here, as well as standard model, which is one, and the measurement from lab, which was also shown on the previous page. So it's really nice, and with the level of precision that we have, we are really trying to constrain the standard model as fast as possible. One very interesting measurement for BSM is right looking at the Z2 invisibles. So this is of observation of electroweak Z plus gamma plus two jets, and this is observed with 5.2 sigma. And you can see here the invariant mass, the dijet invariant mass distribution for different control and signal regions. The fiducial measured pulsal cross section is 1.31 femtobarn, and the signal strength is around 1. And this is really nice because this is the first observation of Higgs of Z2 invisible in this channel. And on the other hand, if we look at the leptonic channel, so where Z decays into two leptons, electrons or muons, we have actually observation with more than 1 sigma, and we can 10 sigma, and we can measure the cross-section, combine the electroweak plasticity cross-section very precisely, and the value is given here. So it's 20.6, and the level of precision is better than 10%. One very interesting observation that I want to mention. So we know that LHC is a proton collider, but on the other hand, we can use it also as a photon. So we have these very rare processes where we have two Ws, photon-induced WW production. So in the final state, we have opposite sign electron and muon, which comes from the Ws. So what is interesting here, right, because the main background for this process is quark-induced WW production. So in order to try to distinguish our signal, so the two Ws coming from the photons, we are actually using this exclusivity selection, which means that we are looking for that we are selecting our event so that 1 centimeter around the diphoton vertex, there is nothing. So right when you zoom in, so this is our dilepton vertex, and then we put a cut that 1 centimeter around it, there is no any activity. And this is how we are actually reducing the quark-induced double production. So this process is observed with 8.4 sigma, and the other cut that we try to separate the exclusive tau production from WW is that we also have a cut on invariant transverse momentum of the electron-muon pair above 30 GeV. So here you can see that we are really dominated by the WW processes. If we go lower, it's gamma gamma, and the measured it's tau, and the measured cross section is 3.3 sigma. So we are still here at the level of observation. If we look at the semi-electronic vector boson scattering, so we have 1 lepton missing a T and 2 jets, which are consistent with the W or Z decay. So here we have 2 channels. We have an ID electron, the muon channel, and as a dominant background, we have W plus jets or TT bar, which is estimated from different control regions. And this is actually a first evidence of a vector boson scattering in the semi-electronic channel. You can see that the level of our signal compared to the to all the other backgrounds. We are using again we have 2 topologies, the boosted and the nominal one, and you can see here how the boosted topology looks like compared to data. The measured signal strength is 0.85, and again, we are just looking into this process with more data, we can be more precise. Looking into vector boson scattering, so right here we have many different channels, so W gamma, WZ or Z gamma, and you can see that we have enough data to look into differential distribution. So we are starting to set the DFT limits and starting to probe the anomalous party gauge couplings. As an example of dimension 6 EFT, we can, there is a measurement that I want to present here, which is a combined interpretation of 4 different analyses. So leptonic WW, leptonic decay WC, the 4 lepton, and the Z2 vector boson fusion of Z to 2 leptons. So in a way, we have 4 different inputs. And we have 33 operators, and we can, so in this case, the linear and the quadratic effects are constrained separately, and the limits are set to 15 different Wilson coefficients, and you can see the limits of the Wilson coefficients on the right-hand side. There are no deviations from the standard model expectations, but this is really giving us a first look into the standard model electroweak fit. And as a last analysis, I want to say a few words about the observation of the WWW, which is the first observation of this process at the LHC. So here we have same sign electron muon plus 2 jets or more, or we have a different channel where we have 3 leptons. And then we have 2 separate BDTs to separate the 2 lepton or the 2 lepton channels for signal background. And here you can see how this this looks like for a different signal at the control regions in different channels. The measured cross sections is 850 femtobars, and you can see that we have a large statistical uncertainty. So this is still at the level of observation, from the few different channels, the combined expected significance is 8.5 sigma, and you can see that we even have a channels which are enough for observation by themselves. So it's the 2 lepton channel or the same sign to means, and the expected signal strength is 1.66. And to summarize, so I try to present very selected results from the atlas and the CMS at the LHC regarding electroweak and top measurements. So we are trying to finalize all the results with full run 2, and the majority of the results presented in this analysis have full run 2, but still we are some of the result, we are still working on analysis to analyze the full run 2 data set. And right, we are switching the gear towards the differential distributions and trying to do the EFT interpretation of all these measurements. And here, right, the picture that I showed at the beginning, how I want to structure these different processes at the LHC. Right, so if we add more data and we try to analyze from the run 3, the measurement, analysis which are now in the evidence regime will switch to measurement, and then, right, if we add more data, even into the precision measurement. So you heard the previous talk, what are the prospects with a much larger data set and a different energy from high luminosity LHC, and keep an eye on the full list of the Atlas and the CMS results. And again, I put the links here so that you can hear you can see the very fruitful program that we have at Atlas and CMS. That's it. Thank you.
That's the second speaker. Any question or comment? If there is no more question, let's thank the speaker again.
Thank you.
The next speaker is Qinghong Cao. He will talk about top quark physics.
So sorry, I'm trying to learn how to switching my screen, but can you hear me?
I can.
Okay, can you see my screen? Can you see my talk?
Okay.
Okay, yeah. Thank you very much for inviting me to give a talk to review the top quark physics. And so we know the top quark is very special in the standard model. It's a heaviest particle in the standard model. We used to ask the question why top quark is so heavy, but after the Higgs boson discovery, we realized top quark is the only natural fermion in the standard model because its mass is close to the weak scale. And we are starting to asking the question why the other quarks and the leptons are so light. But at the weak scale, there are 4 particles, and these 4 particles form a triangle. And by testing the triangle relation, we can testing the standard model at the weak scale. For instance, the Higgs boson is the only it's only one self-interacting particle in the standard model, but its production is involving the top quark inside the loop. So from the Higgs production, we can measure the top Higgs Yukawa couplings, and also the top quark gate boson coupling can tell us the equivalent theory. From all this side, we can measure the top quark physics to test the electric weak theory. And the top quark is also appear in many new phase resonance decays. For instance, the single top quark can appear in the double prime decay, and the D prime can yield top quark pair signals. And more exotically, there are triple top quark productions in some new phase extensions, for instance, like the technical particles. And finally, there is many particles can give the collected signature as the top quarks. In this slide, I summarize the most recent development in the field. And I apologize if I missed your talk here, if I missed your work here. And for as a good probe, the top quark provide a very rich collected signature. But unfortunately, there is no clear signal in any bound searching experiments. So we have to believe if the new physics is there, it must be very, very heavy. So in the rest of my talk, I will focus on the 2 indirect search for the new physics beyond the standard model. The first one will be the effective couplings, which means the new physics will somehow will modify the gate boson and the Higgs boson coupling to the top quarks. And the second of my talk will focus on the effective operators. So, but in order to searching for new physics through effective coupling or effective operators, we have to know the standard model background very precisely. But fortunately, we are in the year of top quark precision at the Large Hadron Collider. So my first topic, so the first part will be the top quark precision in the standard model. From the previous slides, from the previous talks, you have heard that both Atlas and CMIS collaboration has measured the different top quark production channels very precisely. And this figure shows different production cross-section are very consistent with the theory predictions. So it's a very remarkable achievement. But we have to answer, but in order to get a more reliable theory prediction, we have to go beyond the one loop, two loop theory calculations. And here is the recent result reported by the CMIS. They have measured the top quark pair unit mass close to the TD+ ratio. And from their measurement, they have seen their data is deviate from the next leading order and the next leading order theory prediction. And recently, Professor Yang Lilin has, with his collaboration, has calculated the QCD column correction as ratio, which resummed the next two leading powers to the order. And from their calculation, it shows once we include the next leading order QCD correction with the ratio next to leading power resummation, and that's the net contribution, we bring the theory prediction very close to the CMIS result. And this new predictions also help to resolving the tension between the different top quark mass measurements. And also, the single top quark production is very sensitive to the new physics in the electromagnetic sectors. And Gao Jun, Jun Gao, Huaxing Zhu, et al., they have done many calculations recently to push the single top quark production into the next leading order accuracy. And in their calculations, they have calculated the differential cross-section of the single top quark production with the top quark decay completely as the full next leading order. And their calculation has shown as the next leading order, the 5-flavor scheme has a less scale dependence, which is perfect for the precision measurements. And from their modeling of this single top production as the Large Hadron Collider, they have shown the single top quark channel can also be used to measure the top quark mass, as shown in the right-hand side. And these measurements can improve the top quark mass measurements within the 1 GeV. And once we searching for the top quark new physics, the first starting point will be look at the top quark effective couplings. And here I show you one example, seeing that using the tree-level channels to searching for the effective coupling of top quark to prove new physics. And this channel is for top quark productions. And actually, this channel has been proposed almost 30 years ago by Barger, Stringer, and Phillips. Back to that time, the top quark is not discovered yet, but they have calculated the QCD correction. The QCD induced the production rate. And later on, people have added in the electroweak interactions because there are 4 top quarks in the final state. So the interference is very complicated. And in the year 2016, I and my collaborators had proposed to using this 4 top quark channel to measure the Higgs top quark interactions. The basic idea will be the Higgs and top quark interaction, the coupling is roughly about at order 1, which is at the same magnitude as the strong coupling strengths. And because the interference is so sizable, so as you can see from this table, the purely the Higgs mediated contribution to the cross-section is roughly about 10%. And so by measuring the 4 top quark production very precisely, one is able to extract out the top quark Higgs boson interaction from the cross-section measurements. And later on, this is a group of gentlemen. They have done the calculation. They have calculated the next leading order QCD correction to all these processes, including the interference effects. And the CMS and ATLAS collaboration has measured the all-topic part productions by comparing the upper limit of the cross section. One is able to obtain the upper limit of the topic part coupling, like the top will be less than 1.7 times the standard model value times the standard model values. And we also show that the for topic part channel is also sensitive to the CP property of the topic part Higgs boson couplings. And with the new precisions, one is also able to measure the topic part effective coupling inside the loop. For instance, let's a Z boson coupling to the topic part has not been verified experimentally. Even though we can produce the TT bars through the Z boson mediated diagrams, but unfortunately it suffers from the QSD background from topic part pair production. So there is no able to we are not able to directly measure the ZTT couplings. And so we have to look for the ZTT associated production. But in this work, we demonstrate that we can measure the Z boson polarization in the ZD pair production to measure the ZTT effective couplings. At the tree level, the ZD pair production can be induced by either the QQ bar initial state or the gluon box diagrams and the triangle. But in the standard model, the ZD pair are mainly transverse polarized. That's simply because two reasons. For the QQ bar, as a large event region, because Z boson can be treated as a longitudinal gauge boson at Eton. So this coupling will proportion to the light product mass, therefore is highly superized. For the box diagram and triangle diagram, due to the unitarity cancellation, these two diagrams cancel each other. So the ZD pair in the gluon fusion channel is mainly in the transverse polarized mode. And the longitudinal mode is the cancellation can be seen by this equation. As you see, the 180 is chosen to be 1/2. So therefore, there is strong cancellation there. But in the new physics, once the AT is modified, it deviated from standard value. So there is an enhancement in the transverse polarization of the Z boson in the final states. So we are able to, when we can make use of this fact to measure the ZTT effective couplings. So this is the correct simulation result. And the X and Y axis shows the deviation in the vector and the axial vector components of the ZTT gauge couplings. And the same band are shown as the ZT jet measurements. And the black one is shown the ZTT, the associated production. And the magenta band shows the polarization measurement from the gluon fusion. As you can tell, because this one, the gluon fusion channel is sensitive to the axial vector couplings. It's not sensitive to the vector couplings. So therefore, we end up with the two magenta bands. So our result shows the gluon to the ZD pair production channel can be provide additional information to the DTT solid production and the ZT jet productions. And later on, as the large hadron collider, the high luminosity phase can be further constrain the axial gauge boson couplings of the DTT interaction. And the next part I'm going to talk about will be the effective operator analysis in the top part of physics. We have the UA models, but let's assume the new physics is decoupled light. They are very heavy. So at a certain scale, lambda, so we can integrate out all those heavy resonance. We end up with the high dimension operators with the proper Wilson coefficients after running down to the electric scale, and we can compare to the all these measurements. But the analysis, the EFT analysis means that we are going to take the data and compare to the operator set and trying to get the numerical value or the magnitude of the Wilson coefficient. And from the correlation between the different operators, we are trying to get we are trying to guess what kind of a UV model we have been searching for. But this one is highly non-trivial because when we try to make a comparison between the sum of the EFT and the measurements, at the dimension 6 level, there are 59 independent operators. And if we look at this physical observables, like the cross-section or the different cross-sections, and we have to get at least the 59 dimension vector space in order to obtain all those Wilson coefficients. But there is some difficulties that we have to answer. For instance, like the cross-section will be depending on the linear of these operators, which means we take into account the interference effects between the standard model process, the metric element, and the new phase operators. Or this cross-section will depend on the quadratic terms coming from the operator square. But if we take the quadratic terms, so we have to worry about the dimension 8 operators. And second, the second trouble will come from the RG running. And also we need to answer which operator basis we are going to use. The series basis, the quadratic basis, or the different basis. And some operator had to be done with the field and message redefinition. And once we including the QSD high order corrections with all those correlations we are seeking for will remains. And also the operator mixing will destroy all those relations. And in order to answer that questions, I propose to do two kinds of EFT analysis. The first one will be the resonance guided EFT analysis. And here I choose a very, very special example to demonstrate my idea. So the first one, the process I'm looking for is the triple top quark the productions. The triple top quark, if you look at the final state charge, you are going to see it requires at least 1 2/3 charge particle, the proton inside the proton. So therefore, in this channel, the triple top quark production can only be induced by a flavor changing interaction. So there is a flavor changing interaction in this channel. But in order to produce the two top quark in the final state, so this new phase resonance, they have to generate flavor conserving interactions. So the triple top quark is very different in the top quark physics. It requires both flavor changing and flavor conserving neutral interactions. But once we keep this in mind, and we are able to see the blue one is flavor changing. Once we admit this vortex exists, so this one will generate the same sign top quark production. And the flavor conserving interactions will generate the four top quark production. So therefore, the triple top quark production will link with the 2 and 4 top quark productions. So this one, we are able to make a global fit. So this one, and here I just show you the flavor conserving and versus the flavor changing interaction coupling strengths. And the green and the yellow band shows the one we get from triple top quark productions. And the blue and the red curve shows the 4 top quark upper limit. And the blue one shows the same sign top quark upper limit. So, and if we are lucky in this region, and we have to, we can make sure there is a flavor changing and the flavor conserving interactions if we see the deviation in these 3 channels. So this is the UV resonance guided EFT analysis, and that will generate the correlation between the different operators. And the second one will be look at the operator generates the correlation between the single top quark production with and without Higgs bosons. The T-channel single top production is shown in these Feynman diagrams, and there is a strong correlation between this THQ production. There are 2 Feynman diagrams, and we know there is strong correlation because these 2 diagrams are cancelled with each other due to the gauge invariance. But if we look at the single top quark channel without the Higgs boson, and let's ask what kind of dimension 6 operator will modify this production channel. And there will be this kind of new physics. For instance, we have this weak magnetic dipole-like operators, and shown in in this diagram. We can also have this double prime induced interaction, and also the actual quarks induced interactions. And this 2 can come from this operator O5Q3. And also we can have this double prime induced fault-forming interactions. But if we ignore the quadratic term of the operators, let's keep only the linear terms in the operator. And we are going to see, so these two fault-forming operators will generate the same kind of interference with the model contribution. The only difference coming from the color factor. So, and let's start to treat them as one operator. And from this one, only these three operators will modify single top part production. So, and we can see the production rate will be just once we take this three operator take into account, and this will be the production cross-section, the dependence there. And so if we look at this operator, and if we look at this UV underlying UV physics, and we see that if we require this only one Higgs boson in the single top one, in the single top quark production, we require both two Higgs bosons develop their wave to become the vacuum expansion values and to generate the single top production. But if we demand only one Higgs develop wave, so in that case, that will give us the single top quark production with the Higgs boson. So this is a strong correlation generated between the two channels by developing two or one Higgs boson developing their waves. And of course, in the single top quark with the THQ production channels, there is a more operator getting involved. For instance, like this kind of operators. But this operator can be constrained by the current electric wave precision measurement and the single Higgs measurements, and even the Higgs boson decay. So, and we from our analysis, we show that only the same three, exactly the same three operators will contribute predominantly to the THQ the productions. Then, and the cross-section relation will be looked at in the bottom. And so we will see there are three operators, and we only have two processes. And it seems that we are not able to give any physical prediction. But fortunately, the single top quark has provided very much richer information for us. For instance, as a large hadron collider, one can measure the single top and the single anti-top quark productions. And one is also able to measure the ratio between T and T bar production. And in addition, the top quark spin correlation can give us this kind of asymmetry measurements. For instance, the charged lepton from top quark decay is highly correlated with top quark spin. And so we can measure the charged lepton in the forward region and the backward region to constrain this operator. So we have the three operators, but we have four processes, four physical observables, and that give us this strong correlation about the THQ production with the single top quark measurements. And if we take the current single top measurements, and that tells us, so the THQ production cross-section should be in this kind of theoretical region. And if we take the high luminosity projections, and the single top quark cross-section should be roughly about 80 femtobars. So, and all this relation will be spoiled by the high order QD corrections. But here I want to point out this relation will help us to check the consistency of the standard model with the consistency of the standard model EFT analysis. And if one look at the single top quark, the high order corrections, and so I have to mention the pioneer work by Professor Lee, and actually to my best knowledge, he is the one who first calculate NLQD correction to the high dimensional operator of the top quarks. And in the year 2005, they have calculated the net linear QD correction to the gluon UT couplings. And later on, including the QC
3 minutes.
Okay, and the next negative linear log retramations, and they also perform the correct simulation. And later on, they also calculate this kind of the NIL correction to the rare top party case. And this June, we have a big loss, very talented young physicist Chen Zhang passed away this June. And in his last work, he has calculated, he helped to develop a dedicated tools to calculate the thermal EFT as the next linear order. And here I just show his result, his study on this kind of 4 top part productions. And in his study, he has shown the Hughes correction of the EFT contribution can be very important due to the operator mixings and also the interference between the standard models. And one have to consider about the QD contributions when do the complete standard model EFT analysis. And also in this package, and this pattern shower and harmonization was full take into account. And in this April, there is a remarkable achievement in the standard model EFT analysis. And this group of gentlemen, they have done the combined standard model EFT analysis. They consider the Higgs, diboson, and top quark data from the current Large Hadron Collider, and they have done their global fit in 50 dimensions, in 50 directions, and they have done this kind of they have done their study in 2 different fitting approach, and finally they demonstrated that leading order correlation can be washed out by the high order QZ corrections, and since my time is running out, so I will not say more about their work. And currently, I think this will be my last page. My summary will be: fortunately, we are in a year of top part precision at Hadron Collider, and with all those precision environments, it's the time for us to think about what we can learn from the data. And the EFT analysis will become more and more important in the next 10 years. That's my personal opinion. Thank you.
Just a second speak. Any question or comment? Questions? If there is no more question, let's thank speaker again.
Okay, thank you.
This session is over.
Okay, so let's take like an 8 minutes break, and we'll start like from 10:35 for parallel session. Thanks.